Hi everyone, we are Group 14, and our topic today is models of water clocks. And our members are Huang Yuting, Wu Zhonghai, and Xiaofang Hao, and I'm Xiaofang Hao. First, let me introduce our outline of the presentation, and I will do an introduction, and then Huang Yuting and I will do mathematical model analysis, and then Wu Zhonghai will do Python simulation, and the conclusion. First, let me introduce clock. A clock is a device used to measure, verify, keep and indicate time. And clock is one of the earliest inventions because of the need to continuously measure the time interval. And after many years of evolution, there are already many kinds of clocks. And now modern clocks can be very small and accurate. We can see clock in our daily life very often. But our theme this time is relatively old. And our theme this time is clepsydra. And what is clepsydra? A clepsydra is namely a water clock. A clepsydra is a device that uses gravity to make water flow to measure time. Water can flow into or out of the container, and the height of the water in the container is a one-to-one function of the time from the beginning of the water's start flow. And there's many kinds of clepsydra. And the first one is the simplest, outflow clepsydra. And the outflow clepsydra, which is the water flows out from the container. And then we can know the time from the surface and the scales of the container. And the second one is inflow clepsydra, which is similar to the outflow clepsydra. And the differences between them is outflow clepsydra is to know the time by the scale of the container pouring the water, but the inflow clepsydra is we know the time from the scale of the container to accepting the water. But our topic today is we want to explain the differential equation. Use differential equation to model the polyvascular clepsydra. And Yuting will explain the principle of polyvascular clepsydra later.
So in our report, we are going to explain the phenomena of the clepsydra in series like this. One will flow into another, and practical is look like this one. And now I'm going to explain the math behind the one single clepsydra. In case one is inviscid case, so it just looks like this. There is a hole in the bottom, so we can know the rate of water flow out of this container. Just use conservation of mechanical energy. So the loss of the potential energy is rho gy, and turns out it will become kinetic energy like this one 1/2 rho v squared, and v is simply the rate of the lowering water level multiply this a. A is the area of the container, and pi r squared is the area of this hole. So we can change the formula like this form and get this form. The next case is the viscosity domain case, and we assume our container just like this picture. It has a thin tube attached to the bottom of the container, where the water will flow out from it. And then we use Hagen-Poiseuille's law to solve this question. What Hagen-Poiseuille's law says is that when the water tends to flow through a thin tube just like this one, its pressure will lose independent to its volume flow rate, which is Q, the length of the tube, which is L, and the viscosity, which is mu, and the radius of the tube, R. And the formula looks like this one. And then we adjust the formula to this form. Since position A and position C have the same pressure as atmosphere, so P is referred to the above delta P, which is the pressure difference between point B and C, the two sides of the tube. And the pressure of position B is just the pressure of atmosphere plus the pressure of the water in the container. So P is equal to rho G Y, and Y is independent of T. Following, we substitute the rate of water flowing out, which is Q, to the rate of decreasing of water level multiplied by the area of the container. Finally, we can solve the differential equation, since dy over dt is equal to a constant multiplied by y. And to simplify the question, we change this formula to this form. Since this equation is nonlinear, so we don't discuss this case in our report. Instead, we discuss this case and solve this equation. So we try to solve the polyvascular clepsydra of viscosity domain case. Since we assume that all of the vessels are initially full, and that they all have unit height and unit volume, our full set of questions is like this one. Which y1 of t indicate the first container's water level, and yj of t is the jth container's water level. So we have all of the initial value 1, since we set it to unit volume and unit height.
Yuting just showed the viscosity dominant case to us, and now I will solve the differential equation of the viscosity dominant case. And first, we need to solve the differential equation of the first vessel, which is y sub 1 of t, and we know that d sub y sub 1 of t dt equals to minus y sub 1 of t, and the initial value of this is y sub 1 of 0 equals to 1. So as we can simply solve the differential equation, we can get a solution is y sub 1 of t equals to exponential to the power of minus t. When we solve the first vessel, we can now proceed to the second vessel, which is dy sub 2 of t dt equals to minus y sub 2 of t plus y sub 1 of t. This is the differential equation of the second vessel. And we can solve this differential equation by variation of parameters. So we firstly solve dy sub 2 of t dt equals to equals to minus y sub 2 of t. Then we can get the general solution. Y sub 2 of t equals to sigma of t multiplies exponential to the power of minus t. And we treat the constant sigma as a function of t. And because the constant will change by time, and we will solve it later. Then we plug this equation into an inhomogeneous equation. Into this equation, we get d sigma of t exponential to the power of minus t dt equals to minus sigma of t exponential to the power of minus t plus y sub 1 of t. And then we apply in the product rule. So we differentiate e to the power of minus t, so we get this term, and then we differentiate this term and multiply this term, so we get this term, and equals to the original these two terms plus together, and we cancel this term, so we cancel the term minus sigma of t multiplies exponential to the power of minus t, then yields we can get this equation, and then we solve this equation, we get sigma of t equals to t plus c, and c is a constant, and because all the vessels are full of water initially, so y sub 2 of 0 equals to 1, so we can note the sigma of 0 equals to 1 too. Thus sigma t is 1 plus t, and the y sub 2, we can know the equation of y sub 2 of t equals to 1 plus t, and multiplies exponential to the power of minus t, and we repeat the previous procedure to find j equals to 3, 4, 5, 6, 7, 8, so we can know y j of t, we can know all the yj of t, we can know all the vessel differential equation, and we can know the relationship between water and the container.
So Xiao just get the yn of t equation. And now I'm gonna show the Python simulation result. We import pyplot and numpy to use their functions. Next, we set the range of t to 0 to 20 by linspace. Next, we simply type in the functions of y1 to y5 from the previous equation, which represents the first to the fifth vessel. We set the limits of y to 0 to 1 in the plot because we want to set the initial height of the 5 vessels to 1, and observe the time it takes to drop the height to 0. And just use pyplot to plot this curve into one graph and labeling them from y1 of t to y5 of t. Then we can obtain the result. The original question that we set was how nearly constant the flow from the nth vessel is, and for how long. The flow rate out of the nth vessel will be constant if yn of t is constant. We simplify the last equation in the previous page, we got this formula. That is, since yn of t is initially equal to 1, the flow rate will be nearly constant as long as yn of t is approximately equal to 1. Then this term should be very small when n goes to infinity. We can see from the formula that when n is bigger, the time it takes for yn of t to drop to 0 is also getting bigger, which means the more constant yn of t will be. Moreover, when n approaches to infinity, the time it takes for yn of t to drop to 0 also goes to infinity. And now, we can also easily see from the plot that yn of t with bigger n drops slower. That is, the height of the bottom vessels will drop slower, meaning the bigger n we have, the more stable water clock we have. Finally, I will explain the crude estimation of the linearity of the nth vessel. By Taylor's theorem, we know that this sentence is correct when n and t are big enough. And in our water clock analysis, n and t are not small, so this formula should be applicable throughout our water clock analysis. We simplify yn of t with this formula. We can obtain that yn of t is always larger or equal to 1 minus t to the power of n divided by n factorial. And the following lemma will give us a rough estimate of how long yn of t remains close to 1. For example, suppose we want to know when yn of t equals to 0.9. Since this occurs after the time at which t to the power of n divided by n factorial equals 0.1. The lemma tells us we can just substitute c for 0.1 and we can obtain the t when yn of t is equal to 0.9. This crude estimate tells us that our model has at least a basic feature that we expect from our water clock. That is, the drainage time of the n vessel clock is essentially linear in n. And that's our midterm representations. Thanks for watching.